Hi guys, well we've got an ATX power supply here. It's nothing special, just a 250 watt ATX supply, but it doesn't work. So I thought, well, it'd be interesting to see why it doesn't work and if we can fix it, yeah, actually economically, so you know, practically for hardly anything at all really. But there again, you can't put a cost on knowledge, so maybe it's worth repairing it, you know, because just the experience of learning is definitely worth something. So, what's wrong with it? Well, let's zoom out the camera a bit and let's have a look. Yeah, so basically the power supply doesn't switch on, that's what's wrong with it. I'll show you. This is just a hard drive. I'm just using this as a load. It's always a good idea with an ATX power supply to give it at least some load. The hard drive doesn't actually work. It spins up, which you know gives me an indication that there's power on it, but it's not a functional hard drive. But it's useful just to put a bit of a load on something like this. So we'll connect the power. Okay. I've put this up so you can see the fan, yeah, in the power supply itself. Let's just check if the fan actually, yeah, the fan's freely rotating, so should be operating, yeah. It should be operating. So what I've done is, as I always do with these kind of unknown quantities, yeah, is I've connected a light bulb in series with the power lead. You've seen it before if you've watched the channel, but it only takes a moment just to do it. You can skip this, guys, if you've seen this before. So we have AC coming in, live neutral, yeah, and we have AC going out, live neutral, and the neutral's just connected like so, and the live goes via a light bulb. So here I have a light bulb into neutral, and on this one it's I think it's a 65 watt halogen. This only works, by the way, with proper filament light bulbs, not with LED bulbs or fluorescence. Yeah, it's got to be a proper light bulb, you know, an old school light bulb. So that's connected like that, and then we have from here a switch. Okay, and when the switch is open, the live is connected via the light bulb. So the reason for this is if we connect something here that's short circuit, what do you think is going to happen? Well, an electrician would tell you the light bulb will turn on because you've got a circuit. Yeah, you have a circuit, so the light bulb will turn on. That's what would happen. So it's basically to stop things going bang. Yeah, if it doesn't, if this comes on bright, then we have a short. If it doesn't come on bright, we don't have a short. If it doesn't come on at all, we probably have an open circuit load or something that's drawing almost no power. What you'd expect with a power supply like this one is when you first turn on, the bulb will flash as the main capacitors inside here charge up, yeah? And after a few seconds that would go out or go very dim. At which point you can switch this switch close and just bypass it. It's done its job. So not only is it a protection device, it also gives us a good idea of what's happening, yeah? So you should make yourself one of these. All you really need is, you know, it's just a... You can make one using, let me show you my other one, you'll see how it's made. So I have one built onto the Variac over here. This one is another one that I made, so you can see how it's made now. Effectively, this is just like a double socket backing. This is a blanking plate, and I've drilled a hole to mount the light bulb here. Power comes in, and then the power comes out. So this is a UK socket, yeah? So you power on and off here, and this is the switch, which switches between going through the light bulb, which is limit or direct, yeah. This one has a 60 watt bulb. This has a 60 watt bulb here, and I also have wired into it in parallel with this one a 100 watt bulb. So on this one I actually have two light bulbs here, yeah, like so. This is the second bulb, yeah. And this is 60 watt and this is 100 watt. So with this I can either have like 160 watts allowing power through, or just 60, or just 100. Some devices draw too much power, so this would just sort of light up anyway. And if I want to adjust it between 60 and 160, I just unscrew the bulb, yeah. Or if I want 100, I just take this bulb out. So that's it. You've seen it. Apart from these bulbs are getting hard to get hold of, so buy yourself a few and keep them spare. Get them off eBay or somewhere. You probably don't find them. You find them in shops here, but I don't think you do in the UK much anymore. So that's the light bulb. Those of you who've seen that before, skipped, hope you're back to join me now. So we've got a load. Yeah, we've got power. We connect into the light bulb, which is up here, and you will see on the camera. Yeah, you'll see what happens when we switch this on. Okay, here we go. Yeah, so the light bulb flashed bright once and went off. The fan isn't spinning, but again, it's not started. You wouldn't expect it to, but it's drawn power. That's behaving like a power supply ATX should. Yeah, it should do that. So it's not open circuit, and it's obviously charged the capacitors. Yeah. So let's try and start it. I'll leave it this way so you can see the fan. You can see the fan in there. So this is just a couple of old meter probes just connected together. So I've got a probe on both ends of the wire, yeah, and it's great for shorting things together. So to start an ATX power supply, we take the green, yeah, and we connect it to one of the blacks. I think this will stick down the hole. No, but I can hold it. Okay. So we've got the green, yeah. We can switch this now to just mains directly. We don't need the limiter in anymore. It's not going to go bang. And we can just connect this to one of the black. As you can see, nothing happens. Yeah, nothing's happening. We got nothing. So let's have a look to see two things. One, we should have 5 volt standby on the purple wire. Because a motherboard needs that standby voltage to turn this on, yeah. And secondly, on the green wire, we should have 3 volts or 5 volts. It will vary a bit, but we should have a positive voltage, yeah. So let's have a look what we've actually got. So black lead to one of the blacks, doesn't really matter which one. All the blacks are the same, so it really doesn't matter which one. And well, that's our 5 volt standby. I'd hardly call that 5 volts. It's 3.64. So there's a problem. The 5 volt standby is low. It's not. It's lower than it should be. Yeah. What's on the green one? 3.19. You can't say if that's right or wrong. This pin, the motherboard sends a signal by connecting this pin to ground to turn the power supply on. So that I'm not particularly. I mean, it could be right, it could be wrong, but this one is wrong. So the problem with this power supply is we've got no 5 volt standby. We can also say it is running because you have got some voltage here, yeah, but not correct. So now we're going to have to switch it off. That'll take a few seconds to discharge, and open it up and have a look to see what's going on inside this. Okay, let's do that. Now you should know, you need to know, inside power supplies like this, and notice I've disconnected the power now, there'll be 1 or 2 large capacitors on the power input, which could be holding up to sort of towards 350 volts. More if this has PFC, power factor correction, could be nearer to 400. And we need to be sure that those capacitors have discharged, otherwise this is dangerous, yeah. But the fact is, the power supply seems to be running to some extent, and let me just go back on here now, on the 5 volt standby. This should be draining away to 0, yeah. It's still going down, so obviously there's still charge in those capacitors, yeah, still charge in there. What we can do to be absolutely safe is just wait, yeah, just wait until that actually drains away. Let's just wait for that. Okay, I paused the video because I thought it would take a while. It went all of a sudden, so all of a sudden the capacitors have discharged and there's nothing much coming out of here. So we know that is now becoming safe to work on, yeah. But I'll still check the the capacitors once I've got it opened. Right, let's get rid of that. We don't need that just for now. Let's see what we've got inside this. Actually, let's just find a little plastic tub. It's got a few capacitors in, nothing else. And let's just put all the screws in here so we don't lose any. Yeah, that's good practice. You don't want them rolling around on your bench either. So when you've got this thing open up, you don't want a screw that you've left lying around accidentally going under there and shorting something out. Yeah, we've got enough problems it is with this power supply without shorting stuff out on it as well. Okay, so it's open. We're in. A ballast. This is a cheap power supply. I don't believe this has any power factor correction PFC. Not well. It does because that's what this ballast is doing, but it's not. It's not like an active PFC circuit. If you watch the other video, do you remember the other one? If you didn't watch the other one, I'll link it on this and go have a look. But the other one had 3 of these big heat sinks. Yeah, first one was power factor correction. Second one was driving the switch mode transformer, and the third one was the rectifier diodes for the outputs. Okay, so that's got a big thing on there. Can't easily unscrew it because the screws, if there are any, are underneath the label. That's a bit of a pain. Right, okay. These are the 2 large capacitors I was talking about. Yeah, the ones that we need to be wary of because they can hold a voltage charge, and depending on the fault on this, they can hold a voltage charge for a long time. If it wasn't running at all, this can stay dangerous for a really long time. Yeah, so we need to know about this. Probably the best way and the easiest way to see if there's any charge in those capacitors when it's like this is to measure across the positive and negative of the bridge rectifier. It might not give you 100% answer, but it'll probably if you see voltage there, you know there's voltage in these. Yeah, so let me zoom this in so you can see what I'm doing. Yeah, there you go. So these 2 capacitors, by the way, I've just looking, they are 470 microfarad, 200 volt, yeah, and there's 2 of them. So these will be in series. These will be connected in series, yeah. And the 2 will be connected across the rectifier, bridge rectifier. And I can see that the outer legs are marked plus and minus. So what I'm going to do is I'm going to check the voltage. Let's put the meter where you can see it. Well, let's put the meter there, where you can see it. So yeah, I'm just going to check if there's any voltage across this bridge rectifier. I don't expect there will be now. Plus to minus. Well, there's 7 volts, so there is still voltage there. So you can see this is a good way without taking the circuit board out, which if these are highly charged, again, could be dangerous. I mean, you could leave it for a few hours. But there you can see that there's about 7 volts across them, yeah. So that's is it 7 volts or 1 volt? There's a bit of a glare on it. No, it's 7. It's 7. So yeah, we know this is safe to take apart, and this is showing to you, this is proving to you how long we've been chatting about this. What, like almost 10 minutes in, there is still some charge in those. Okay, let's take it apart. It's just going to be a few screws in here holding the circuit board in, and we need to take the circuit board out. It's not possible to work on these with the circuit boards in the casing. So these we have to take them out. Not too difficult. The plastic tub here. Two. Three. I'll put the soldering on because I'm going to need it. I'm going to need the soldering iron. This will just clip up out of here, I would say, yeah. Find the screw, there it is. Sorry if my head was in the way there, guys. Just getting this out of here. So what soldering this to? Oh, there's a screw in the back here that goes into this heatsink. Bit of a novel idea, that. How can we hold that still? Just put a screw in through the back. It does the job. Circuit board's loose. So this is the wiring from the fan, yeah. So we have to take this cable tie off here. We need to separate this from all the other ones. So let's get rid of these. That's probably the one that holds that on. It goes through both of them. But we can slide this out. Yeah, it's out. So that's for the fan. Made quite cheaply. They haven't even bothered to put a socket and plug here. It's just soldered on. So we'll probably have to unsolder that, or maybe just disconnect the fan. Unbolt it. And then obviously in here at the front, this is your power coming in, yeah, your live and your neutral, and again that's just soldered to the board. So we have to get this out and desolder this. Easiest way is probably going to be just to desolder them from the power connector here, yeah, where they're coming in. Let me just get a torch so you can see it. Yeah, here, so where you've got the live and the neutral coming in here, we'll desolder them from the connector. Okay, needle nose pliers probably. Told you I was going to need the soldering iron for this, didn't I? Get a bit of solder. Okay. That doesn't want to give it up easily either. It's off. It's off. I'd probably been better cutting that. In fact, I might end up cutting the other one to get it out easily. Yeah. Let's try with the pliers again. Again, there's another little plastic zip tie on this one, so that can go. One of them things, yeah. And let's unsolder the other one. Again, not easy, but we'll have it. Get a grip on that one. Okay. Try it from the other side. Hitting the other side of the wire where it goes through the hole in the power IEC connector. Yeah, it's off. Let's give it up in the end. Okay. So this will now come out of here. Right. So we now have it. We can disconnect this load at the moment. We don't need that in the way. That can go. Don't need them anymore for now. Right. What have we got? let's have a look at what we have. Let's zoom in on this one. Shall I? Yeah, I'm going to disconnect this fan as well. Just get it out of the way, yeah, so it's easier to work on this. When you do this, guys, make a note which way around the wires were. Yeah, so the red one is this end. I'm going to mark it in a minute. If I can find I can't find a red pen, so I'm going to mark the inside one with a black, yeah. So that's black. We know which one it is now. We can just clean this up while we go along. And now let's see what we can see, yeah. Okay. There you go. So that's out the way. Don't need that for now. Don't need the hard drive for now. This is still attached, but I don't think that's going to be too much of a problem. Okay, let's zoom in. So what have we got? Well, we can see these are the two large capacitors, the ones that we were saying hold a charge. We know now they discharge because I was checking on the bridge rectifier, but they may even have a very small voltage left in them, about 1 volt. This is where you need to check if you want to make sure it's not in a dangerous condition, yeah, across the big capacitors. There's one there, where's the other one? Where's the other one? Further behind is the other one's here. And the two are effectively in series. So this end's positive. This end's negative. 2.5 volts, yeah, nothing to worry about. Unless you want to measure some accurate resistances, it's probably a good idea just to discharge those capacitors actually. If you want to discharge, and when they got a low voltage like this, the easy way is just to short them with a screwdriver. When you got a high voltage, you should use a resistor to do this. Not suddenly discharge them, because you get a big crack of the flash. It might make you jump a bit, but it's not good for the capacitors, yeah, to do it. So there we go. Right, now they are discharged. It's near as damaged. Okay. So looking underneath it first. First thing you'll see is a big gap down here, yeah? A big gap here. And the only thing going across the big gap between the two is this here. This is a Opto Isolator, yeah? So this side will have an LED inside it, and this side will have a photo transistor inside it. There's no electrical connection, but by altering the brightness of the LED, you can alter the conduction of the transistor on this side, yeah? And send a control signal between the two, yeah? We've got 3 transformers. 1, 2, 3. A big heatsink here, and on the big heatsink here, a couple of they marked Q1 and Q2. Q is a transistor almost always, 99 times out of 100, maybe 100 times out of 100. Q denotes transistor. These will be 2 MOSFETs, yeah. These will be driving this big transformer, yeah. And on the other side of the big transformer, this heatsink has, you can see them down here, there's 3 rectifier diodes, yeah. Almost certainly one will be on the 12 volt, one will be on the 3.3, and one will be on the 5 volt, yeah, coming out of the transformer. So where does the 5 volt standby come from? Because that's what you're interested in. Well, it looks like on this one we have here a control IC, yeah, and the chances are, we can check from this control IC to the transformers, the chances are this control IC is driving this transformer, yeah, and this forms a little switch mode power supply for the 5 volt standby, yeah. Coming out the other side here is a rectifier diode, yeah. So that would be converting the 5 volt standby AC out of the transformer back into DC, yeah. and that would go into the 5 volts. And in fact, you can even see the purple wire comes down here, which is near to this diode. So that makes sense that this power supply controlled by this chip and drives a 5 volt standby. Yeah. So what controls these big FETs that drive the big transformer? Well, there's no other chips around here, but there is one over here. Yeah. Let's have a look to see what these chips are. This one, which I think is a little power supply, and this one. Yeah. Let's have a look at the part numbers and let's see what they actually are. This one is marked DM311. You might even be able just about to see that. This one's marked DM311. Yeah, and then BH50. So let's make a note of that one. DM311. Yeah. This big one is marked a funny little symbol 3528. Looks like an F symbol. Looks like an F. Yeah, and then 3528. Yeah, you can see it now, can't you? 3528. And then the other numbers are like date codes. So it looks like some sort of F and then 3528. Let's make a note of that. Let's have a look, see if we can find these online. Yeah, let's see if we can find a data sheet for these 2 chips. Okay. Browser's taking a little while. Let me just check I'm actually online. Yeah, one moment. Okay, yeah, I'm online now. I don't know what it is. I have fibre optic at the workshop. It's symmetrical, 600 megabit up, 600 megabit down. Like, you know, 1,200 megabit total. One thing you do get the Canaria hours is cheap. Bloody fibre optic is like €48, you know, for like 600 up, 600 down. But for whatever reason, when I turn this computer on at the first time in the morning, sometimes it just won't connect, even though the internet's working. The other computer will go on, and I have to reboot it. Yeah, Richard, you'd fix that, shouldn't you? So, the DM311. Let's have a look at this one. Okay, so it's a power switch. Oh, Fairchild does it make. That's interesting, because the other chip on there that said 3528 had a funny F logo by it. I'll bet they're both from the same manufacturer, whoever's built this thing, you know. So this is a chip. It's a power switch, pulse width modulator. So we can find the data sheet for it. Here we go. There we go. Even with the speed of fibre optic I've got here, sometimes, I mean, he's just throttled by the speed of the website you're trying to open the data sheet from, yeah? Come on, give it to me. Didn't? Oh, tell it to stop and then it did. Okay, so, yeah, it's an FSDM311 integrated pulse width modulator and sense FET. So it's basically it's what we thought it was going to be. These are the pins of it. So this is a switch mode power supply driver. Grounds, power, feedback, and VSTR probably drive startup, and drain. Yeah, so it's the drain of the FET. So you find the typical circuit for it. Some examples. Tells you how to use it. Yeah, here's a typical sort of schematic. Yeah, so you can see the chips here. The drain, the FET's driving this coil. This is the primary of the transformer. Yeah, so power in. This switches to ground. So this is your primary, drives the primary. This is your secondary. This is where we can see a diode the other side of that transformer. That goes to the load. And there's a separate little winding here that effectively powers this chip. So when this chip first starts up, let's see if we can see it. there'll be a startup. The startup resistor might be built into it actually. May well be built into it. And this must be able to power it back somehow. Let's have a look. V2. Does it even say what that is? That's probably the. Can I see V2 anywhere here? That'll be the drive. From that there, that'll be power back into this chip. Okay. Oh, probably connects there where it says VCC. You can't just even see it on here. Yeah. This is the Opto Isolator I mentioned, the photo transistor, and this comes to the feedback. So this monitors the output voltage of here, yeah, and then when there's enough, it changes, it lights up the LED, which effectively turns this transistor on and changes the voltage on feedback. So this now knows it's got enough voltage. If it's too low, this goes out, tells the feedback, and it gives it a bit more drive. So that's it. That's that little chip, yeah. And this, I guarantee, will be driving the 5-volt standby, yeah. Let's have a look at the other one. What was the other one? It was we used a Fairchild. Let's just search the number first. 3528. Datasheet. Yep, 3528 National Semiconductor. I'll bet this thing's made by lots of different people as well. KA 3528. Can we even find this? Is this it? No, that's an LED. 3528 datasheet. An LED driver. Okay, let's try, because we think it's Fairchild, yeah? Because the other one was Fairchild. And from the logo. That says a KA3528. There. SMPS, switch mode power supply driver, yeah? 3524. It's got to be here somewhere. Fairchild, what we thought. Can't see 3528. I can see 3524. I'll bet it's a very similar thing to that. Let's look at the 3524. Switch mode power supply driver. It looks like ours. It's got 16 pins on. 1, 2, 3, 4, 5, 6. No, I was like 20 pin or something like that. Okay, so I don't seem to be able to find the exact datasheet for that. So I have one more look. 3528. Fairchild 3528. Well, it's saying the KA3528. Fairchild. Let's try that. KA3528. KA3528 datasheet. See what that is. It's not this King Bright. This is LED lamps. LED lamps. So obviously there's two completely different things with the same sort of part number. No, I still can't find the exact datasheet for this thing. Portsmouth controller. Again, Fairchild. Try this one. Is there a datasheet? Yes. No, that's a... Oh! 12 pin, 24 pin. How many pins has ours got? No, that's a memory. That's a RAM. That's a different chip. Okay, so we can't find a datasheet. We can find something similar, 3524, which is switch mode power supply control. But I think that's all we need to know. Let's go back onto the workbench and let's see what we've got here. let's see what we've got. So this is the board again, and we can pretty much work out how this works and make a couple checks to see if we're right, yeah? So I'm saying that this controller here, the DM311, drives this transformer, yeah? Coming out of here, there's a rectifier which goes down to the 5-volt standby here, yeah? On the purple wire. This is our F3528 that we don't seem able to find the exact data sheet for. 5, 6, 7, 8, 20 pin, yeah? But it's Fairchild, and we've had a 3524 which had 16 pins, but that was a switch mode power supply control. It makes sense that this is also. So this will be controlling the main transformer, yeah? We've also got down here, by the way, can you see here? This is the Opto Isolator, and this is coming back to the DM311, which we just saw on the data sheet. That's how it has feedback, so that makes sense. That all makes sense that is the 5-volt standby controller, and also will power this. So this, when it switches on, needs to drive these transistors, yeah? And this big transformer. But these transistors and the big transformer are this side of the divide, yeah? That's what the other transformer's for. So this will be driving, depending if these are MOSFETs or bipolar transistors, it will either be driving, if the bipolar will be the base, yeah, or if the MOSFETs will be the gate. So this drives this transformer, and the other side of the transformer, primary, secondary on this side now. This side of the transformer drives the base of these, which then drive this big transformer, and your output voltage comes over here. If that's the case, we should be able to see this transformer go into one of the pins on here, yeah? And we should be able to see the secondary, this side of this transformer, going to the base of these, yeah? And we ought to also be able to see from the output of this diode going to the standby. So let's have a look. Out of interest, and I think we don't need to know this to fix it, but let's have a look out of interest to see if that's what we really have, yeah? I'll just put it onto the continuity mode. Okay, on continuity mode. So it bleeps so you can see it, yeah? So we're thinking this rectifier diode here is driving 5-volt standby. See if it does. Could go through a voltage regulator before it does, but it might just go straight to it. 5-volt standby. Yep, comes from there. So, yeah, purple wire. So we know that's 5-volt standby. We know this is driving it. This will also be powering somewhere, this chip. Either directly or indirectly. Yeah? No, that's the resistance 10 ohms. It probably does drive it just via a resistor or something. That would make some sense. This transformer, the middle one, should go to the gate of these. Okay, so let's have a look at that. Output of this one in the middle, which looks like they're here. That's the big one. Where's the small one? It's a bit further in. Probably here. This is probably the primary, and these are secondaries by the looks of it. In fact, you can see that this does go into this. Yeah, it'll probably go to the gate as well. This will probably be almost short. Yeah, that one goes to there. So it looks, yeah, that does appear to drive these big transistors. Another pin on it here. Yeah. So from this transformer, we're definitely driving these big transistors on here, which are driving the output. So we now know how it works. Yeah. You understand now what we have here. Yeah. Let's. Sorry if these videos are long, guys. I just want to make sure that people definitely understand this. Yeah. Let's just zoom out a little bit. Okay, so this is what you've got. We've got live and neutral, yeah, coming in. One of them's going via this big choke. The big coil thing that I said was actually attached to inside the lid, yeah, this thing, yeah. This effectively acts as a power factor correction, but it's a passive one, not an active one. It's either old power supply or a cheap way of doing it, yeah. This then goes to your bridge rectifier. I won't do all the diodes, but basically you've got bridge rectifier here, AC, and then coming out plus and minus DC, yeah. This then goes to your two big capacitors, a 200 volts, what were they, 470 microfarads to there, yeah. That goes to there. This we'll call ground, yeah. We'll call this negative ground. Coming from the DC here now, you've got, this is your DM311, yeah. Ground, yeah. There'll be resistors in here, whatever, but it's connected like that, yeah. From your DM311, the output drives the small transformer, yeah. This is the bottom one, slightly bigger than the middle one. That drives this transformer, yeah. Coming out of here, diode, yeah. This here is, and by the way, up to here, this is not ground. This is what's called hot ground, yeah. This is half mains potential, yeah. This is the big divide on the circuit board between the two halves, high tension and low tension, hot and cold, yeah. So this is not ground earth. This is ground earth here now. So from here, this goes to 5 volt standby, and it also goes to the 3528. 3528. Yeah, it's written there, yeah. This now drives the middle transformer, yeah. Okay. This is driven from this chip, pulse width modulators, yeah. Transformer. This side of the transformer goes to the two big transistors, yeah. These are your two big transistors on your heatsink, yeah, that are driving the big transformer, yeah. And from here, this gives you 5 volts, 12 volts, 3.3 volts, yeah. So there'll be several windings on this transformer. There'll be 3 secondaries probably, one for each voltage, yeah. And these big transistors, obviously these go to hot ground, yeah. They go through the primary of this to the 300 volts, yeah, into the transistor one, that's what it like, yeah. And the drive of these two effectively comes from this transformer, not connected like that, but that's how it's working, yeah. So this is standby power supply, and this is your controller powered by standby, which then drives the transistors that drives the big one. That's how it is, yeah. That's basically what we have. What's wrong with it? First of all, if that was clear as mud, ask me and I'll do that again, yeah. What's wrong with it? Let's zoom in on it. So we know 5 volt standby is working, it just doesn't have 5 volts on it, yeah. That's 3.5. So we know this must be working, yeah, but it's giving the wrong voltage. Do we have a low resistance to ground on the purple wire on the 5 volt standby? I doubt it, but yeah, we need to check that. Let's just be sure. Let's put the meter back on, yeah. Do we have a low resistance to ground on the purple wire? Purple wire. No. That was a capacitor charging. No, don't have a low resistance. So why is this not giving enough voltage? Well, this is controlled by the Opto Isolator here, yeah. And this, the LED side varies its brightness depending on the output voltage. So when the output voltage is correct, this is lit to the exact right extent that this signals this to tell it it's got enough output voltage. And when you draw more power on the output, it needs more drive. It varies the brightness of LED, maybe goes dimmer, and this says, oh, you can see that's gone dimmer, so it needs more power, and it tells this to send more power through this transformer. It's altering the width of the pulses in this, driving this. So the narrower the pulses, the less output you get. The wider the pulses, the more output you get. Yeah. So that is connected onto this side. Yeah. And on this side, we can see we've got a rectifier diode, and we've measured from there to the purple wire. And then we've got capacitors. Yeah. To smooth, you know, the AC pulse AC come out of this back into DC. Yeah. But look at the capacitors. What's this shit? What is this on the top of this capacitor? Yeah. And not only that, what is this top of this capacitor? I think you can see, yeah, slightly domed, yeah, compared to this one. That's a good one. That's flat. And obviously, because I've told you that's a good one, and you now, I didn't even tell you that's a bad one. That's a bad one. The capacitance of this is probably gone. Yeah. I don't know if you can hear that. This is like knocking on a wall to find the cavity. Yeah. Can you hear that slightly hollower sound? Yeah. The microphone closer. That's probably dried up. Inside here is like an electrolyte fluid, yeah, and that'll be dried up. And while we're at it, not only is that one dried up, but this one I'm tapping here, which I said is a good one. I'm not 100% if that hasn't slightly bulged as well. And let's have a look over here because we've got more capacitors. Well, that one's suspect. The shit's just come off it now, but that's bulged, that's gone. And there's another one down here. This one looks bulged. And this one we got a bit more of that black stuff, and that one looks bulged. So what we have on here is a handful of very, very suspect looking capacitors, yeah? This one in particular smooths the output from this transformer, and this Opto Isolator is connected into this circuit and monitoring the voltage here. And if this capacitor isn't working properly, you're getting like ripple on here, voltage spikes, yeah? So the voltage here is probably spiking higher than it should be, and it's probably signaling this wrong. So this thinks there's enough output when there isn't, and this is not driving it correctly. So there's every chance if we replace the capacitors on here that look like they're knackered, and test the ones that don't look like they're knackered, then we can probably fix this. And I'm pretty sure I must have some salvaged capacitors of the right value. We can test capacitors. So let's start to desolder all the capacitors on this board, the bad ones, and I may as well go for these two because that looks bad. This looks a bit suspect. This is bad. This one looks a bit suspect. It's bulged. This one is bad. And while I'm at it, I might as well try that one because it's next to it. Yeah. So 1, 2, 3, 4, 5, 6 capacitors on here. We're going to take off. First thing to do is going to be to take a photograph. And as I remove these capacitors, I can print this and I can write on the print the value of capacitor that went there, so we can't forget what's come from where. Yeah. So let's just get a picture of that. I'll do two. One from here. Right. I'll go and print that out, then let's start desoldering capacitors. So, there's my photo. I took the photo and just decided it was quicker to just draw it than it was to actually print out the pics. So these are 1, 2, 3, 4, 5, 6. These are the 6 capacitors, and basically that refers to this. So it's easy. I can see where they are. Yeah. So we've got 1, 2, 3, 4, 5, 6. Sorry, 5, 6. Yeah. So what we're going to do is now start to desolder these capacitors. Some will come easier than others because you get this white glue on them. Yeah. so you probably have to cut away that glue to get some of these out. They're quite easy to remove, so if we go for, say, to the first one, which is here, yeah, we can just see where the legs are, which I can see looks like they're here. Yeah, it looks like they're there. It's just to add a bit of leaded solder and literally just pull the capacitor out of the board. As long as you've got the right pins, it should come easily enough. And then once I take it out, I'll make a note on my photo yeah, of the value of the capacitor and which way round it was. So I've just got some solder there on the 2 pins. Yeah, and we're just going to come in here now and just warm one up, tilt the capacitor one way, warm the other, tilt it the other way, as if it's out, yeah. So there's our capacitor. We can see which way round it was. Quite nicely marked actually, so the little black line down there, that's the negative end. That's the way I just took it out. So this one is allegedly 2200 10 volts. So I'm just going to on my picture of which one it was, yeah, it was the one by the heatsink, this one. So 2200 10 volts, yeah, microfarads, and the negative is towards the heatsink. Oh, phone, okay. Sorry about that. Sorry about that. Just a phone call. So that's what I'm doing. I'm taking them out and making a note. Yeah, we'll do one more and then we'll go and I'll just do them off camera. It'll take me a few minutes. You don't need to be watching every single one. This is the next one. Yeah, which is here. And you can see this is held in by all this guns. Yeah. So what we have to do with this one is effectively break the gunge away from it. Yeah. That's it. It should be loose now. Yeah, it's now physically loose from the guns. Yeah, so that should come out. We can always put some fresh guns back on later if we want to do. Okay, so next one is here. By the looks of it, looks like these two. It's a matter of sort of like looking at where it goes, and looks like it's these two. Could be wrong. Looks like it's these two. Okay. Let's see if we were right. Yeah, I've rocked it one direction, the other direction. Well, I might be wrong on that one. That's exactly where it is. Let's have another look. Oh, it looks to be in the right place. This appears to be held in by all this mucky, gluey stuff. Yeah, let's have another go. See if it's here. No, I think that's in the wrong place. I've now got a solder bridge there, we'll soon fix that. Bit of flux would help actually. Just to fix that, let's fix it now before we forget it's there, yeah? We've made a solder bridge here. Oh, here. Yeah, I'm going to have to clean that off with a little bit of braid. That's it. Yeah, let's have a look to see where this thing actually is. See the purple wire. Yeah, it looks like this capacitor is being held in by the glue still down this side here, yeah? So I need to just break this glue here away from the capacitor because it's not going to come out otherwise. Let's get rid of that. It's horrible stuff, this. Now it's loose. I think I was on the right pins. I think it was just the glue that were holding it in. Okay, let's have another go. Get hold of the capacitor from this direction, I think. And yeah, let's see if we can get this one out. I think that's coming. Yeah, it's out. So I was on the right pins. It was just all that gungy stuff, yeah, hold it in place. This one is a 1000 microfarads, 10 volts, yeah, 1010. And again, I'm pretty sure it'll be marked on the board. Yep, so the negative end is here. Negative end is here, yeah. Okay, so you've seen me do 2 of them. Oof, didn't make you seasick on that bit of video. I'm now going to remove the rest of them, and we'll continue when we've got all the capacitors out. Okay guys, so I've got all 6 capacitors out now. This is my photograph, yeah, and I've just marked the black on the negative end where they're positioned on the board. I've made a note of the values they were, so I know the polarity of the value. Some of them were green capacitors, a couple of them were brown, so I've just made a note which ones were brown. I can always look back at the photo I did take, because there may be some difference, you know, when we come to replace these, if we need to replace them. So let's have a look at them first. So ESR meter and the capacitance meter, yeah. Put the ESR meter on as well. Yeah, you can see that, can't you? And we're on the 0 to 1 ohm range, yeah. So let's have a look at this. This is the biggest one. Look at this. This one's a 2216 volt. So this range only goes to 2000. This goes to 20,000, yeah. 200,000, I think it's 20 millifarads, yeah. 20,000. It goes to 20,000. So what's this one reading? This is one of the ones that looks okay, yeah. Black. 2.5, 2.6. That looks to be okay on there. And just go on to the ESR meter. I expected this to read very low. Let me just zero it first, so I'll short the two together, yeah. And press Press 0. I must just get some more reads for this. It's close enough, I'm not too bothered about the exact reading. How's this one reading? That's reading like that. Reading like it's got a bit of charge in it. Actually, it's giving me a negative reading. I'll just short the. And that'll be charged from this capacitor's meter probably. Yeah, that looks like a good low ESR capacitor. Let's put that one there. Let's have a look at another one. This is one of the ones that looks like it's sort of bulged on the top, yeah. Black to the negative again. Let's have a look at this one. See what this one reads. 0.23. This should also be 2,200. I'm on the 2,000 range now. It's reading 200. Yeah, that's reading like a tenth of its value, its capacitance. It should read. Let's look at the ESR meter. That's reading like open circuit. Yeah, that's a bad capacitor. And this is visibly gone, yeah, so that's a bad one. Let's have a look at the other four. Another 2,200. Let's see what we've got. This one looks like it's bulged again. Not as bad as the other one, but it doesn't look good. Black to the negative again. Okay, that's reading like 680 when it should be reading 2,000. So Not as bad as the other, but not good. One moment. Sorry about the interruption. So the capacitance is low, so it's bad. So look at the ESR. The ESR is high. It's more than 1. It's bad. I'll change the mode on this actually. Let's go to the 10 ohm mode. So let's see if we get a reading on it. Yeah, we see 1.59. Yeah. Whereas that first good one that looked good, this one that looked good was reading almost 0. Yeah. So that's the one. Another. That's 2 bad capacitors, and one that's probably good. Let's have a look at the other ones. What got here? It's a brown one, 2200 again, 10 volts. Check its ESR. What we got the ESR meter. The ESR is reading high. Physically, it's very slightly better. This one looks almost okay, but it isn't. You can see that it isn't. ESR is high, yeah. Unless these brown ones are just high ESR anyway. Yeah, reading 400 microfarads rather than 2200. That's bad. Another one, same value, 2200. Reading 400 microfarads, yeah. ESR will be high. Yeah. And this one again, just, yeah, this one's gone. You can see in the middle there. That's bad. This is the last one. This looks slightly bulged to me. This one's a 1000 at 10 volts. So let's have a look. Was that reading 0? Check that connection. 300, yeah, it's reading 300. Again, it should be 1000. And this one is 2.7. Again, it's high. Okay, so we have 5 bad capacitors there. 2210 volts, 2216 volts, and the 1010. I've got replacements for the 1010 here, but the 2200s I don't have. So I will order some. Take a few weeks again, but I'll upload. You can see what the problem is with this, and there's a very good chance if we replace these capacitors, it'll work. It's not really worth the expense of replacing it, but I think for the experience, you know, the fact we're gaining some experience from this, it is worth. So I'll order some capacitors. Let's see how much they are. Let's have a look. Let's have a look before we go. Okay. That's what AliExpress says. I might as well replace them all with 16 volt rather than messing around with 10s and 16s, because you can put a 16 in where a 10 came from, yeah. $2,200 microfarad 16 volt. Oh, high frequency, 2,000 2 to 50 PCs, €1. What comes in this here for €7? What do we get here? Oh, all sorts of things. So 2,200 at 16 volt. See if we can find 2,200 at 50. No, we need lower than that. We could put 50s, but it'd be too bulky and there's no point, yeah. 2,200 at 25, we could use those. Can we find some 16 volt ones? Yeah, 16, 100 of them. 100 of them. €7.80. 506 reviews, 450 orders, so people are obviously happy to order these. Okay, so for €7.80 I can get 100 of those, so I'll order those, and that means we've got plenty of them in stock, and we can probably use that to replace a lot of capacitors in the future, to be quite honest. Probably use one motherboards as well, actually. So okay guys, that's for that one. I'll upload this today, and I'll see you soon. See you now guys, bye.